Assalamu alaikum, everybody. This is our last lecture in the course, inshallah, and it is on approximation algorithms. So here is the outline. First, we explain what is approximation algorithm. Then we look at what is called performance ratio, and then we take two examples of approximation algorithms, namely the Vertex-Cover Problem and the traveling salesman problem. If you recall, in our last lecture, we mentioned these two algorithms to be NP-complete. Okay, both the Vertex-Cover Problem and the traveling salesman problem are examples of NP-complete algorithms. So you don't have an efficient algorithm for them. However, in this lecture, we're going to show how you can come up with an approximation algorithm for these two problems. All right, let's get started. What is approximation algorithm? There are many important NP-complete problems. As we discussed in the last lecture, we saw several examples, meaning there is no fast solution or no efficient solution for this type of problems. And as we mentioned in the last lecture, there are three ways you can attempt to go around this problem. One is, if the input is small, then you can go for the exponential solution. It might be just fine if the input size is small. You may also try to solve the important special cases that can be solved in polynomial time. Okay? Or you can try to find a near optimal solution to the problem, okay, in polynomial time. An algorithm that returns a near optimal solution is what is called an approximation algorithm. Okay, so this is the objective of this lecture, to show us how we can come up with this approximation algorithm. And we're going to try to do that with two of the examples that we said were NP-complete in the last lecture. Now, before we do that, let us try to define what is called approximation ratio, rho of n. Define the cost of the optimal solution as C star, and the cost of the solution produced by an approximation solution to be C. Then the approximation ratio, rho of n, is defined as the maximum between C over C star or C star over C. Now this depends on the problem actually, if it is maximization or if it is minimization. We shall explain the detail in the next slide. Okay, but it's going to be one of this ratio. Approximation ratio is either C over C star or C star over C, where C star is the cost of the optimal solution and C is the cost of the approximation solution or the approximation algorithm. Okay, now the approximation algorithm is called rho n approximation algorithm. So for example, if the ratio is 2, then the algorithm which gives you this cost C is called a 2 approximation algorithm. All right. In fact, both the two examples we're going to see in this lecture are 2 approximation algorithms because the approximation ratio is 2. Okay. Now for maximization problems, the relationship between the cost of the optimal solution and the cost of the approximation solution is like this. Because of course the optimal solution will have the maximum value. The approximation algorithm will definitely be less than or equal to that. Okay, so C is between 0 and C star. Therefore, in that case, the approximation ratio is defined as C star divided by C. Always the bigger one divided by the smaller value. Okay, so this gives the factor by which the cost of an optimal solution is larger than the cost of the approximation solution. Okay, what about for minimization problems? For minimization problem is the opposite, because definitely the optimal solution will have the minimum value or the minimum cost. So whatever approximation algorithm you come up with is likely to be greater than the cost of the optimal value, which is the definite minimum. So in this case, we define the approximation ratio as C divided by C star. Okay, so this ratio will give the factor by which the cost of the approximate solution is larger than the cost of the optimal solution. So this is why in the previous slide we said the approximation ratio is maximum of one of these two ratios. As you can see clearly, it depends on whether the problem we are considering is a maximization problem or a minimization problem. If it is maximization, then this will give you the approximation ratio. On the other hand, if it is minimization, then this ratio C over C star will give you the approximation ratio. So a one approximation algorithm will produce an optimal solution, therefore, because the ratio will be 1 over 1. If you are able to reach 1, then you have found a solution that is exactly as efficient as the optimal. So it's usually more than 1 actually. So large approximation ratio implies that a solution can be much worse than the optimal. All right. Okay, so let's take our two examples then, starting from the Vertex-Cover problem. Okay, so let us take the first of our two examples, which is the Vertex-Cover problem. A vertex cover, as we defined in the previous lecture, a vertex cover for an undirected graph G, which consists of a pair of V and E, V being the set of vertices and E being the set of edges, is a subset of the vertices V prime. So V prime, a subset of V, is called the vertex cover. Such that if UV is an edge in G, then either U belongs to the cover or V belongs to the cover. This is a formal definition. If you recall how we defined it in the last lecture, is that every edge in G should be incident to one of the vertices in the vertex cover. So this is exactly what we are putting here. If you take any edge UV, then either U belongs to the vertex cover, meaning the edge will be incident to U, or V will belong to the vertex cover. So again, the edge will be incident to one of the vertices in the vertex cover. So this is the definition of a vertex cover. The size of the vertex cover is the number of vertices in it. Okay, so how many elements are in V prime will give you the number of vertices in it. Now, an optimal vertex cover is a vertex cover with minimum size in an undirected graph. Okay, so the optimal our vertex cover is the one with minimum size. So in the case of vertex cover problem, the optimal solution actually is a minimization, the minimal value. All right. So the vertex cover problem is to find an optimal vertex cover in a given undirected graph. This is the problem as we stated it in the last lecture. Now we're going to come up with an approximate vertex cover algorithm, and it is given here. Okay, it is called approximate vertex cover. It will take G as input, G being an undirected graph. Okay, here is how it goes. It defines a set C initially to be empty. This set is going to be the cover. Okay, and it defines E prime initially to be equal to the set E, all the edges in the graph G. Then in a loop, as long as there are more edges in E prime, so you're going to be taking edges one by one from this set until it becomes empty. So as long as there are edges in our E prime, let UV be an arbitrary edge from E prime. So pick one edge from E prime arbitrarily or randomly. Okay. Add the vertices connecting that edge to your set C. Okay, so C will contain both the vertices in your arbitrary edge that you have picked from E prime will be added to the set C. Okay, now once you do that, remove from E prime every edge that is incident to either U or V. Okay, so remove from this set every edge that is either incident to U or V. And then you repeat. Okay, so you pick another edge, assuming the set E is still not empty, you're going to pick another edge, add both its vertices to your cover C, and then remove from E prime every edge incident to the edge that you have just taken. Okay, eventually, of course, the set E prime will become empty, so you're going to return C as your vertex cover. To illustrate this, let's take an example graph. Okay, I'm just repeating the algorithm here for us to easily follow what is happening. So suppose we want to find a vertex cover for this graph based on this algorithm. Okay, so assume we initialize our set C to empty and E prime to be all the edges in this graph. Then we pick an arbitrary edge from the set E prime. So suppose it is this one we take. Okay, so mark it as being selected. And according to the algorithm, we should put both the U and V that this edge is connecting, add them to our cover. So here we are highlighting the vertices that are accepted for the cover in white. Okay, so B and C are going to be both added to the vertex cover. Then the algorithm says remove from E every edge that is joining U or V. So that is joining B, or that is incident to B or incident to C. So clearly we're going to remove this edge from our E prime because it is incident to B. So the edge that has been removed is being put here in dotted line. Okay, similarly this edge is incident to C and so is this one. So both of them should be removed. Okay, so this is our first iteration. Now we repeat, pick another edge. So you can see our E prime now has just 1, 2, 3, 4 edges left. Now pick one of them randomly again. Okay, suppose it is this one we have taken. So according to the algorithm, add the vertices that edge is joining to the cover. So the cover will now have the vertex E, and it will also have the vertex F. Okay, now remove all edges incident to either E or F. Clearly this edge is incident to E, so we're going to remove it. Similarly, this edge is incident to F, so we're going to remove it. Okay, and then we repeat. Our set E prime is still not empty because there's still one more edge left. So we're going to pick it, and when we pick it, we will add the vertices it is connecting to our vertex cover. So both D and G will be added to the vertex cover, and this time there are no edges to remove. Okay, so the algorithm, or this algorithm, will give us A, B, C, D, E, F, G as the vertex cover for our original graph. Okay, as you can see here, this cycle is showing us the vertices we have selected as the vertex cover for the graph G. Okay, it seems like all of them except A. Now this we call approximation algorithm, because actually this is not optimal. This is not optimal. In fact, I'm going to show you the optimal solution for this graph. This is the optimal solution, optimal vertex cover for our graph. Okay, if you take only B, E, and D, then you will see that all edges in the graph are incident to one of these vertices. See, this is incident to this is incident to that, this is incident to E, this is incident to D, incident to D, incident to D, incident D. Okay, and this one is incident to E. So all the edges in the graph are incident to one of these three. This is the optimal solution. This optimal solution is the one we say so far there is no algorithm to find it. Okay, if you are given a solution, you can check and verify that it is valid, as we just did. But so far, no algorithm has been found that can give us this optimal solution. What we have here is just an approximation. So this shows you how to find or how you can approximate a solution. Obviously, this algorithm is just going through the edges one by one, so at most it's going to be the order of the number of edges. Okay, so this is basically shows you how to find an approximate algorithm or approximation algorithm for a particular problem. In this case, the vertex cover problem. Okay, now what we are going to answer next is what is the ratio of our approximation algorithm for this vertex cover problem. So we have a theorem here. It says approximate vertex cover is a two approximation algorithm. In other words, the ratio between the result returned by this approximation algorithm and that returned by an optimal solution is 2. This is the approximation ratio, and we're going to prove this theorem. Proof. So let A denote the set of edges that were picked by our approximation algorithm. Okay, if you can notice from the graph here, the edges that are picked by our approximation algorithm are this one that are shaded or that are drawn boldly. So this edge connecting BC, the edge connecting EF, and the edge connecting DG are the ones selected by this line in the algorithm. Select an arbitrary age from the set of ages E prime. Okay, so we're going to denote the set containing these ages as A. A denote the set of ages that were picked by the approximate vertex-cover algorithm. Now we observe that no two ages in A share an endpoint. Okay, again I'll show you. If you look at these two of the three edges, the vertices they are connecting, they are completely disjoint. We don't have an edge that share a vertex with another edge. Okay, so the endpoints are completely distinct. So what does that tell you? It means the number of vertices will be twice as the number of edges that are picked by the algorithm. In other words, the size of the vertex cover is going to be twice the number of edges that are picked by the algorithm. Here we have 1, 2, 3 edges, and we have 1, 2, 3, 4, 5, 6 vertices. Okay. Okay. So that's the observation here. Observe that no two edges in A share an endpoint. Now, to cover the edges in A, any vertex cover, in particular an optimal vertex cover, must include at least one endpoint of each edge in A. Alright? Any vertex cover, forget about the one that will be returned by this our approximation algorithm. Any vertex cover you take, because the edges that are in A are distinct, and it is joining the vertices in the cover. So we are saying the cover, to cover the edges that are in A, any vertex cover you take, in particular if you take the optimal vertex cover C star, it must include at least one endpoint of each edge in A. Therefore, we can say that the number of vertices in the optimal vertex cover is definitely going to be greater or equal to the number of edges in our set A. Okay. Now, on the other hand, the algorithm picks an edge for which neither of its endpoints is already in C. Therefore, we can say that the number of elements in our vertex cover is twice the number of edges in the set A, as I already explained. Okay. Now, based on this two relationship, the optimal vertex cover is definitely greater or equal to A. And we have here now the number of vertices in the near optimal cover, which is C, is 2A. So replace the 2A with the C star based on this relationship, and you see that your C is less than or equal to 2C star. Okay, yani if you look at it, if you replace the A, okay, C is equal to 2A. So, and here we say that A is less than or equal to the number of elements in C star. Therefore, 2A will be less than or equal to 2C star. And this proves our theorem, because you see that the number of vertices in our vertex cover is less than or equal to 2 times the number of vertices in the optimal cover. Okay, this is the end of the theorem. The last example we're going to take is the troubling salesman problem. Given a complete undirected graph G that has a non-negative integer cost associated with each edge uv, find a Hamiltonian cycle A, which is a tour of G with minimum cost. Okay, we explained the traveling salesman problem in the previous lecture. So this is the problem here. As we explained before, this is also an NP-complete problem. There is no efficient solution so far. Okay, obviously the cost of our tour here, or the cost of the Hamiltonian cycle, will be the cost of all the edges in our tour. Okay, so for each edge in A, get the cost of that edge and add it to the sum. The total sum will be the cost of the tour. Okay, so TSP, traveling salesman problem, is an NP-complete problem, as we explained before. And our objective here is to find an approximate solution for it. Not for it actually, but for a special case of the traveling salesman problem. So we're going to consider TSP with triangle inequality. TSP that satisfies the triangle inequality problem property. Let's explain what that means. So we shall develop an approximate algorithm for a special case of TSP, one that satisfies the triangle inequality. Okay, let's see what that means. The cost function C satisfies the triangle inequality if all vertices U, V, W belonging to V can be related like this. So the cost from U directly to W is less than the cost from U to V plus the cost from V to W. So instead of going directly to W, we pass through V first, and then from V we go to W. So if the relationship, if you take any three vertices, if the relationship is like this, then the vertices are set to satisfy the triangle inequality. So this is the idea, and we want to come up with an algorithm for this special type of traveling salesman problem, the one that satisfies the triangle inequality. Here is an example of one. Say example of cost functions that satisfy the triangle inequality is the Euclidean distance in a plane. What is the Euclidean distance? The Euclidean distance is simply the distance in a plane between 2 points. So just ordinary distance from B to A without attaching any special value, just the distance. Okay, for example, from Jubail to Dammam, what is the distance? We're talking about the distance only, not the time it will take you or the cost it will take you, just the distance. So if you take ordinary distance between 2 points, it is called Euclidean distance. So now Euclidean distance definitely satisfies the triangle inequality. For example, let's say I want to go from A to D. This distance is definitely shorter than going from B to A and then A to D. Okay, yeah, and this is true for any 2 points you take. The distance of going from A to D is definitely shorter than from D to B and then B to A. Okay, the distance from D to E is definitely shorter than D to F and then F to E. So this Euclidean distance in a plane definitely satisfies the triangle inequality. So what we are going to come up is an algorithm, a TSP algorithm that is related to this Euclidean distance. So we're not going to attach any special cost to the edges, just the ordinary distance from one point to another. Okay. Okay, so here, before we do that, we're just confirming that even with the triangle inequality, TSP is still NP complete. In other words, there is still no efficient solution or an algorithm in polynomial time that can give you the traveling salesman solution for even this particular case, where the triangle inequality is satisfied. Okay, now here is our approximate algorithm for TSP with triangle inequality. Okay, the algorithm is called approximate TSP tour. So first, select a vertex R from V to be a root vertex. All right. Compute a minimum spanning tree T from G starting from R using any minimum spanning tree algorithm. We already learned in the data structure course two such algorithms, prims and Kruskal's. So use any minimum spanning tree algorithm to come up with a minimum spanning tree. Let's say that start from R. Now let L be the list of vertices visited in a pre-ordered traversal of your minimum spanning tree. Okay, so we're going to do pre-order. After you obtain the minimal spanning tree, now do a pre-order traversal and take note of the vertices that you have visited. All right. Now return the Hamiltonian cycle H that visits the vertices in the order L. Okay, the order of the traversal. All right. This is best understood with an example. So we're going to take a graphical example, but this is basically, this is what this algorithm is about. Okay, so you pick a particular vertex, find a minimum spanning tree from it, and then traverse that minimum spanning tree. You will come up with a list of vertices. Now generate a cycle based on the order of the traversal. Okay, that cycle is actually a Hamiltonian cycle, and is the one we are returning as our solution. So just add the cost of the edges in that cycle, and you will get your solution. Okay, the cost of the Hamiltonian cycle. Okay, so here is the illustration of the algorithm, where the edges, the weight of the edges are simply the Euclidean distances between the vertices. So given a complete graph, find a simple cycle through all the vertices with minimum total weight. This is the original problem that we are trying to solve. So let this be our graph. No need to put the edges, because edges in this graph simply mean the distance between the vertices. All right. So the first step of the algorithm is to find a minimum spanning tree. Okay. Now suppose this is the minimum spanning tree that we obtain. Okay, you can find a minimum spanning tree using any algorithm, prims or Kruskal's or any algorithm. So this is the minimum spanning tree. As you can see, it connects the vertices, okay, without creating a cycle. All the vertices are connected and no cycle is involved. So this is the minimum spanning tree of our graph. Next step is to now do a traversal. Okay, pre-order traversal from any vertex, let's say from vertex A. If you do that, what do you get? Okay, obviously if you are doing the traversal from A, you go to B. And remember, in pre-order, we keep going deep. So you're going to go to C. When you get to C, you're going to get stuck. So you're going to backtrack to B. Then go to H. You're going to get stuck again. So backtrack back to B. Okay, no other options. So go back to A. And then go to D. Okay, from D, we can go to E. And then we go to F. Backtrack and go to G, and since we have finished, now go back to A to complete the cycle. Okay, so this is the tree walk, if you like, that you will get as a result of doing pre-order traversal of this minimum spanning tree. So we are saying return. Actually, before we return, we're going to eliminate the repetition, because what we have here actually is not a cycle. Okay, because you see, in a cycle you don't repeat a vertex. Okay, so for example here, from B we went to C and then went back to B before we go to H. All right, we're going to replace this with simply this line. Because of what? Because of the triangle property. Okay, going from C to B and then B to H can be replaced by going directly from C to H without adding cost to the graph, because this cost is smaller than this plus that. So this is the idea. If you eliminate the repetition in visiting the vertices, this is the graph you're going to get. I mean, this is the cycle you're going to get. Okay, this is not a cycle because we are repeating the vertices, as I said. So if you use your triangle inequality and avoid all the repetitions, then this is the graph you will end up with. From A we go to B, B to C, and from C we go directly to H. Don't go back to B and then go to H. Okay, similarly from H, you don't go back to B and then to A and then to D. No, go directly to D. Okay, and then from D to E, and then from E to F, F to G, and then back to A. So this will give you a cycle. And the cost of this cycle is the one we are returning as our near optimal solution. All right. Now this is still not optimal. The optimal solution is actually this. Okay, this is the optimal solution. You see here, the algorithm, of course, after H, the next vertex to visit is D, based on pre-order traversal. So the near optimal solution will actually take you from H to D. But that is more expensive than just going to F and then G and then E and so on. You can see, of course, the other point with the pre-order traversal. From the last vertex to complete the cycle, we have to go back to our starting vertex. So this again is very expensive. So this is not optimal. It's only a near optimal solution. This is actually the optimal solution. So this is basically an example of algorithm that can give us a near optimal solution. In this case, we have to add a special property that the edges satisfy the triangle inequality. In this case, they are Euclidean distances, therefore they satisfy the triangle inequality. Right, now we're going to prove, like we did with the vertex cover, that the approximate TSP tour is also a two approximation algorithm. Okay, the ratio is still also 2. Let's try and prove that. First, let us denote by H star an optimal tour for the given set of vertices. So let H star be the optimal tour. Okay. If an edge is removed from H star, definitely the result is going to be a spanning tree. Okay, let's call it TS. And therefore, because of course, if you remove any edge, from this resulting cycle, you have a spanning tree. Remember, the only condition for spanning tree is that there should be no cycle and all edges should be connected. So if you remove any edge, this will be a spanning tree. Okay, so we are saying here that if you remove one edge from the optimal tour, then the cost of the spanning tree that you're going to get is going to be less than or equal to the cost of the tour itself, the optimal tour. Okay, this is one. Now let T be a minimum spanning tree. For example, the minimum spanning tree we obtain at the beginning of that algorithm. Then also the cost of T will be less than or equal to the cost of this tree that we obtained from the minimum tour. Why? Because this is the minimum spanning tree. This is just a spanning tree, not the minimum. So let T be a minimum spanning tree, then the cost of the minimum spanning tree will be less than the cost of this TS that we obtain from the optimal tour. Okay? We can therefore say that the cost of the minimum spanning tree is definitely less than the cost of the optimal tour. Okay, so we're going to take this as equation number 1. I didn't number the equation, but we're going to use this later. So definitely the cost of the minimum spanning tree is less than or equal to the cost of the optimal tour. Good. Now let W be a full walk of the minimum spanning tree, because remember, to obtain our near optimal tour, after we obtain the minimum spanning tree, we have to traverse it completely, essentially doing a full walk. So let W be a full walk of T. Then W will list the vertices when they are first visited and also whenever they are returned from the visit. Okay, what I'm trying to say is, as we saw here, this is basically the W. This is the full tree walk, and you can see the vertices are being visited twice. So first, when you come from A, you will visit B, and then you go to C. Now when you get stuck, you're going to go back to B again. So you see that B is being visited twice. Okay, so this is the full walk tour, and that is what we are calling W. All right, now we are saying that so then W will list the vertices when they are first visited and also when they are returned to after a visit to a subtree. Since the full walk traverses every edge of T exactly twice, we say that the cost of the tour or the full walk, the cost of the full walk is not a tour actually, because there is repetition. In a tour there should be no repetition. The cost of the full walk is twice the cost of the minimum spanning tree, because we visit each vertex twice, okay, or each edge twice. All right, so from our previous slide, we remember the cost of the minimum spanning tree is less than or equal to the cost of the optimal tour. All right, now we have another one. Cost of the full walk is equal to twice the cost of the minimum spanning tree. We can therefore conclude that the cost of the full walk, okay, is less than or equal to twice the cost of the optimal tour. Okay, the cost of the full walk is less than or equal to twice the cost of the full tour. I mean the optimal tour. Okay. However, W is not a tour as we explained. It seems to visit some vertices more than once. By triangle inequality, we can delete a visit to any vertex from W and the cost does not increase. In other words, if instead of going back to a vertex before we go to the next one, we go to the next one directly. So in other words, we make use of the triangle inequality. The cost will not increase. In fact, it will reduce. Okay. So this is just being emphasized in that point. It's a note. If a vertex V is deleted from our full work W between visits of U and W, the resulting ordering specifies going directly from U to W. So basically we are just trying to remove the repetition, but still we will have a connectivity. Okay, we are just following the triangle inequality to go directly from U to W instead of passing through V. Okay, now by repeatedly applying this operation, we can remove from W all but the first visit to each vertex. So let H be the cycle corresponding to this pre-order work. So H is the one that we're going to get after removing all the repetitions. Going back to our diagram, what we are saying is if you remove all the repetition by following triangle inequality, for example here from C, instead of going back to B before going to H, you have a direct line like this, then you will have this cycle. So this cycle is what we are calling H, the cycle that you're going to get after removing the repetition from our full work. This is W, the full work, and this is now H. Okay, so let's continue with our discussion now with the proof. So it says, let H be a cycle corresponding to this pre-order work. Now H is a Hamiltonian cycle because every vertex is visited exactly once. So H is our near optimal solution. The question is, what is the relationship between the cost of H and the cost of H star, which is the optimal solution? Okay. Now, since H is obtained by deleting vertices from the full work, it follows that the cost of H is less than or equal to the cost of W, the full work. Now, this proves that from the previous slide we saw that the cost of the full work is less than or equal to twice the cost of the optimal tour. And now we have just seen that the cost of H, the near optimal solution, is less than or equal to the cost of the full tour. It follows, from these two relationship that the cost of the near optimal solution is less than or equal to twice the cost of the optimal solution. And that is actually what we are trying to prove. That is, the approximate TSP tour is 2 approximation algorithm. The ratio is again 2, similar to what we obtained with the vertex cover. So this is basically the end of the example. We have seen 2 approximation algorithms showing how we can come up with a near optimal solution, even though so far no solution has been found that is optimal. This brings us to the end of this lecture and also the end of the course in terms of the lecture presentations. Thank you very much. Assalamu alaikum.